because back home it's like almost 7 in the morning. I'm still waking up. So I'm pretty sure that you heard the chairman saying words like Ljubljana in Slovenia, but I'm not sure if you know where that is. I'm pretty sure that you know where Stephen, because Stephen is coming from Canada, where Canada is, right? Yes. You know that. Yeah. You know where Slovenia is? No. Okay, good. So I'll use 1 minute of your time and our time to actually do some PR for Slovenia as well. Okay, one slide, just to make sure that you'll get something out of the lecture besides just the technical knowledge, okay? Today I'll talk about a topic in biometrics. The title is given here. I'll read it once again because then I'll, of course, define 2 things for you to actually grasp the idea better. So I'll talk about neural networks, actually generative neural networks, and we'll apply that to face de-identification. And de-identification is the keyword of the talk, actually. Of course, the work that I'll be presenting was not just done by me. It's not a solo project. So those are the guys that work in majority of papers that will be summarized here with me. Good. So how many of you are undergraduates? Okay, master level students. So that together makes 90% of you. Okay, I have to know that in order to, reshape a bit my definition so that you'll better understand everything. Are you all from computer science? Yes. Yes. Good. So we have a very good foundation there. Good. You already heard or listened to the courses on artificial intelligence? Yeah. Computer vision? Yes. Even better. What about biometrics itself? How many hands? Okay, let's say 10, which is good. Good. So we have good foundations here. Everything that I mentioned, from computer science to AI to computer vision to biometrics, is actually part of this title, right? The focus will be on biometrics. Okay. So I said I'll take a minute for PR in Slovenia. Okay, so here we go. Here we go. Yes. Why am I doing that? Apart from introducing Slovenia itself, is that yes, we are always looking for students like you, good students. Yeah. So you actually have to also get an idea of which part of the world we are in. Okay. So. In Lucknow and in general in India, everybody is saying that this is the most diverse country. I couldn't agree more. But we have our own diversity as well. From images like this, lakes, a very famous one in Slovenia, a bunch of castles all around Slovenia, to the seaside, to mountains and skiing resorts, because we are a skiing nation, definitely. Everybody skis in Slovenia. And this is the capital. A small, very small capital, definitely small in terms of India, because if Radim, which is one of the co-chairs of the conference, his opening keynote said that, yeah, I'm coming from Slovakia, which is not Slovenia, right? And we have like a population of kind of an Indian village. I have to say that, okay, if that's the case, then Slovenia has the population of half of the Indian village, right? We are only 2 million, so imagine that, right? Okay. And this is the faculty itself. We moved there 5 years ago. It's completely smart. I mean, sometimes too smart. I'm scared sometimes. Everything is regulated centrally from I won't go into the details. So where the hell is Slovenia? On the map. Right here. Okay, this is Europe, right? Okay, probably what is yellow, well, according to Brexit, I have to cross the UK out, okay? And everything rest is European Union. And Slovenia is right here. Yeah, that small dot. This small dot here, okay? 25,000 square kilometers. Really small. okay? But we have everything, like you saw. Diversity is there. Okay. Enough about the PR in Slovenia, so let's jump to one more slide that will not give you the... won't actually introduce the beginning of the talk, but we'll actually talk about general things that we do in the computer vision lab, which I'm heading at the University of Ljubljana. I have 14 people employed there, and what we do is we move from applications in augmented reality to 3D reconstruction, normally based on superquadrics, and then to biomedical and even meteorological, etc. applications, but the focus at this time is definitely on biometrics, different modalities. I'm not showing all of them, right? But for our talk today, the most important part is this one. It's all about de-identification. So let's jump into the title itself. What is my motivation, first of all? Well, let's first introduce the definition of the de-identification. It's a special kind of so-called privacy-enhancing technology, PET, that removes identity-related cues from the input imagery. That's the idea. Okay, with other words, I could say, I'm anonymizing things. Okay, and I'm trying to do that in a very realistic way. Okay. By the way, Stephen also talked about PET, right? But that's a different PET. Don't get confused. In my talk, PET means privacy enhancing technology. Okay? And we all know, at least in Europe, based on the GDPR, that privacy is really an issue. So we have to take good care of it. Okay. So, said that, when and where to use it? Such technology is actually of paramount importance for ensuring privacy in various services such as, well, you know some of them, like Google Street View, Foursquare, in multimedia data collection shared among government agencies, online video-enabled chats, etc., video conferencing apps, and etc. So you find actually the applicability of the technology in a bunch of real-world cases. Okay, so I'll also introduce a goal. So what is the goal behind this talk and our work actually in this case? At the same time, we want to actually retain certain aspects of the original data and have no ghosting effect. I'll explain both, emphasize things here in a little while. Basically, here I'm talking about the so-called utility function, because to anonymize certain things, if you look through Google Street View, how do they anonymize things? What do they do? They blur or use some kind of a pixelation. And more or less the anonymization is there. But it's questionable, right? We can actually prove that sometimes we can still identify who is there, right? And that is not good. And as far as the ghosting effect goes, this image will give you kind of a clue. This is already a result of 4 methods for de-identification. Perhaps I can start with a question here for you. Some of the images look really real. So which is the original? Which image here is the original photograph? Which one? First one. It could be this one as well, huh? It's very real. And this is generated by our pipeline that I'll talk today with. So this is the original. Yeah, this is the method that is probably based on blurring. This one is based on pixelation. This one is a formal method called K-same. I'll talk about the distinction between the naive and the formal methods later on. And this is our result. And then you can actually see here the ghosting effect I was referring to here. They are combining identities together as we do. But what they produce is something that doesn't really look that realistic. Okay? So this is the ghosting effect. Okay. So what we've done, actually, and I'll try to introduce throughout my talk, is a face de-identification pipeline that actually exploits GNNs, generative neural networks, to produce artificial surrogate faces for de-identification and offers a level of flexibility that I already talked about. So in the generation process, we actually try to incorporate certain utility function because we want to retain certain information that is important for us. Like, okay, I don't want that the system recognize the identity, but I'm very interested in, I don't know, what is the ethnicity of the person? What is the gender of the person? Is he smiling? So emotion. I want to retain that. So it's pretty obvious that I cannot do that by applying blurring, right? Now everything is gone, okay? So I want to retain that information. Okay. Of course, there is a very big diversity in the identification area as well, but within this talk, I'll focus on this branch here. So I'm interested in biometric personal identifiers, and within that branch, I'm focusing on psychological identifiers, and within all the modalities there, I'm of course focusing on faces. Okay? Good. But you can actually see that the whole field of de-identification is quite huge. And you can actually contribute in each of the branches, I mean scientifically. Okay. Perhaps I can shed some light on one additional thing. In many respects, the de-identification is treated like an inverse process to recognition. Okay? Normally in biometry you do the recognition. But I'm still in the field of biometry, but I'm doing the opposite. Okay? But I'm trying to be as convincing as possible with what I generate. Okay? Good. So in this picture, there's a general schematic saying that the data needs to be appropriately de-identified before being shared between relevant stakeholders. Why? To prevent misuse of personal information and ensure privacy protection. This is the main concern, privacy protection. In our case, we are trying to prevent face recognition from, well, video and image data. Okay, it doesn't really matter what kind of source. So at the same time, which is not evident from this image, because yeah, we can actually see that those sketches are de-identified, of course, but at the same time, we want to keep some soft biometrics properties, for instance, like mentioned, gender, ethnicity, age, and etc., and we call that utility function. Okay, so whenever I'll say utility function, just think about, for instance, gender or age or ethnicity, something like that. Or even better, because I'll talk about emotions, as the utility functions think about emotions. Okay. So there are two big groups of existing techniques for face de-identification. The first one is called, summarizes all the naive methods, which I already mentioned before, like pixelation, blurring, black boxing, and etc. But they have a really big problem. Like many of them are prone to various attacks or have other weaknesses. For instance, some of you are definitely familiar with a parrot attack concept. So they are prone to that. Okay? The other one is that they are actually not offering the formal privacy guarantees. So the other group has to do something with that. And it does exactly that. It's called a group of formal techniques that provide upper bounds on the re-identification risk. And we are actually concerned mostly with those methods. They are following certain schemes such as K-same, L diversity, T closeness, or K anonymity. And we actually prove that our method is following the formal agenda, which is good. So it has a mathematical background. Since we are focused on formal methods, the idea behind k-anonymity mechanism is then, in this case, to ensure by replacing number k images from the input set with some surrogate images. So this is the input set, right? And then we actually try to find the surrogate images in order to replace that image for instance, in a video stream. So to preserve some of the information, actually the surrogate images are computed as cluster centroids, as we see in this case, where the k equals to 2. Okay, so 2 images, and this is the average of it, for instance. Okay. So now that we understand the basics of the idea of de-identification, anonymization, we can actually move to the other part of the title itself. And besides the keyword de-identification, there was GNN as well. So generative neural networks. What do we know about that? We heard in the previous talk that the CNNs were mentioned, right? So what is a CNN, basically? So based on the input image, it makes a classification, right? We got an image of the reconstructed image of the captured, for instance, in the previous talk, possible breast cancer, and the classification was tumor or not tumor, right? Okay, so we understand that. So what is the difference between the CNNs and the GNNs? Well, basically, it does the opposite, like shown on this picture. Okay, for instance, this is the architecture that we are actually using within the whole pipeline for generating faces. I will give it an identity from the database, right? And it will produce an image of that person. Plus, I also supply the utility function. And in that case, the utility function is right here. So non-identity related parameter, in this case, I'm making a proof of concept, I'm using the emotion. Okay? So that is what is the input. And the output is actually the image. But this, as you'll see, this is only one, I don't know, fourth of the whole pipeline for de-identification. I'll show you the pipeline in 5 minutes probably. Okay, so to better understand all the needed transformations in order to arrive to the de-identified frame, I'll show you another schematic, this one. This is actually an overview of our solution. The solution is named K-SameNet de-identification approach. It's similar to other K-same algorithms that I already mentioned while mentioning formal methods. Each image in the input set, I, in this case, on the left, is mapped on to an image in the de-identified image set on the right-hand side marked with D. The surrogate faces in D are generated by GNNs that is trained to produce actually identities from a proxy set. This is a proxy set. Proxy set has nothing to do with an input set. But we are introducing it in order to find similar faces from which we will actually extract K, most similar faces, and merge the identities together in order to produce something completely new that actually doesn't exist. Okay? And use that image for the de-identification process. Okay, that's the idea. Okay. So, this is additional thing here on this sketch, right? And I explained it as a proxy database, proxy set of identities. Okay, now we can actually jump to our pipeline. So the pipeline that is given here is a block diagram of our de-identification system. The procedure uses GNN in this step, so this is one fifth of the whole pipeline. Each generated face is then a combination of like I said, k identities from the gallery of that proxy image set that are the closest to what was given to the system as the input. Of course, the whole thing works in real time. So not the learning stage, of course. It takes more time to learn the model, to teach the model, but at the end, it's actually real time when you try to use the model for de-identification. If we go a bit deeper to some of the boxes here, of course, everything starts with an input image from, let's say, a video sequence. Then, first, what you have to do is detect the faces, detect the presence of the people, and you can do that in a number of ways. So, with traditional methods, previous state of the art, or even something like that, which is again deep learning based. When you have that, you extract features for recognition. Why do you need to extract features for the recognition if you are doing the de-identification? Well, it's pretty simple. If I want to get similar faces from the proxy set, I have to have something to compare with, right? So I extract the feature representation of the input image, and then I compare that with a proxy set. Whatever there is each face is represented with a feature set as well. So I'm matching and finding k closest faces. And those are actually the input to my generative neural network, right here. Okay? Plus, of course, if I would like to introduce the whole pipeline, it would be so big that it wouldn't fit nicely on the slide. So I just simplified it. For instance, if you want to retain the appearance-related parameter, so the emotional state, let's say, of the person on the input image, of course you have to have the whole pipeline which will do the emotion recognition as well. Okay? But in this case, I don't have enough room on the slide, so I just said, okay, this is it. Okay? He has to smile, he has to be sad, he has to be angry, whatever. Okay? Good. And then, of course, there's the last step when you actually do the swapping of faces in a way that it will be realistic. Okay? Good. Let's jump to some sample outputs from the GNN. Here they are. So, in this case, we have identity mixing with k identities using 3 different k's. 1, 2, and 4. Okay? Yeah, from the left to right. With an increasing number of identities, the generated faces, of course, always converge towards an average appearance. We can actually notice that even here. Yet, they are still realistic and, what is most important, without that ghosting effect. The first label below each of the images actually refers to generated facial expression, and the second to the identities used while mixing the identities, generating the faces. Okay, so we can actually see, the emotion that was given as the input in this case was happiness, and in this case, angry. Okay, so we can actually see that, yeah, I would look like that if I would be angry. Okay, luckily I'm smiling, which is better. Okay, a few words about the replacement procedure. One of the options that we implemented, not the only one, and at the end, not even the best one, goes like this. This is the illustration of the whole replacement procedure, and we look from the left to right. First of all, we have the Gaussian mask that is used for smoothing the whole swapping process. Then we have the artificially generated face image, then the modified Gaussian mask, because actually you have to be influenced by the input, right? Some kind of a tilt or something like that. Then we have the geometrically corrected synthetic face without the background, the sample frame, so this is the actual input, and then the de-identified frame. Okay, this. Well, if you don't concentrate on the change of the illumination, that frame is very convincing. I mean, even the replacement process is convincing. Okay, of course, the illumination, if you treat it as a problem in this case, can be corrected. And we've done a few other tests with different procedures, replacement procedures that actually corrected that as well. In the bottom part of the slide, you can see the qualitative examples of de-identified frames. So this is the input, this is the output. Input, output, input, output, input, output, input, output, input, output, as the person is coming closer, and this is the actual surveillance video. It's not something that we done in the controlled environment. No, it's the general database for analysis of things going on inside certain buildings. Okay, nothing really controlled. Okay. What we can note here is that the generative network is definitely able to generate really realistic renderings of faces for our purpose, de-identification. Okay. Of course, we have to make a comment also about how successful from the qualitative perspective we are when addressing different facial expressions. So here's an image about that. Okay. Images in the first column represent the original frames from a video sequence in one database. The second, third, fourth, and fifth are actually giving the de-identified frames rendered with different emotional states like happy, angry, surprised, and natural. What we can see here, well, could be kind of a conclusion based on the qualitative results presented here, that our de-identification approach is actually highly flexible and is able to retain all specific aspects of the de-identified faces. This is good. This was our goal. But of course, looking only at the results from the qualitative perspective is never enough. It's just the first step. What you have to add is some kind of quantitative evaluation as well. So here we go. This is first slide of the quantitative analysis. How can we actually go about testing the success of the de-identification? So, first of all, we said, okay, before de-identification, we can employ some state-of-the-art face recognition methods and see how well they perform, right? And the left graph is showing you exactly that. So, the identification rate in terms of CMC curve giving the rank. Okay, rank 1 to rank 20 and so on. So we can actually see that the CMC scores are fairly high. Even for rank 1, for instance here, rank 1 for the reception version 3 is 93.something%, which is good. Okay, so what we've done in the next step is, okay, we de-identified the whole database in the same manner and use the same methods in order to see whether or not they can identify those persons. And the results were those. So they actually had almost no success at all. Okay? So this is actually the proof, the quantitative proof that de-identification works well, not just from the qualitative perspective, but also from the quantitative perspective. Okay, but again, this graph is not showing anything related to the utility function. So anything related to emotions that I showed. So how can I actually check the emotional state? Well, first of all, I have to have the ground truth information about the emotional states in the database. That's the confusion matrix for that. And then I can use that information in order to use our utility preserving model to actually use different Ks, right? And K being number of identities I'm joining together, right? And we can actually see that the results are quite good. So the conclusion here could be that a high expression recognition performance can still be achieved on the de-identified data as well. So I'm actually doing the job well. I'm preserving the utility I intended to. Okay. Good. So instead of, I already made the two conclusions, right? So instead of giving you a list of future work, I will give you two slides that we are already tackling as the future work here. So the first one is this one. It's all about selective phase de-identification. What does it mean? We developed a novel network, let's say, that is able actually to alter the input phases in such a way that automated recognition fails to recognize the subject in the images, while humans still have that power. So we still can recognize the person. Okay, that is one way. Okay. The other thing that we are tackling is on this slide. So it's all about learning privacy-enhancing face representations through feature disentanglement. So the idea here is that, well, I'll start like this. The self-biometric information that is contained in the templates always represents a serious privacy risk. Okay? So we are really concerned with that. So we address the problem of self-biometric privacy enhancement and present certain solution to that, which is again neural network based, of course, of suppressing self-biometric attributes such as, for instance, just gender in face representations without compromising identity cues. So with other words, this is a so-called latent space representation of something that was given on the input. And we want to disentangle that feature space in a way that we only have some certain features which affect the identity, and then other features that, for instance, affect the gender. And then we want to actually conceal the gender, but still retain the identity. And we can actually do that. And this was one of the latest surprises in the last, I don't know, half a year for me. Okay, we can actually do that, and we can do that effectively. So the proposed disentanglement-based approach in this case is actually highly efficient and improves significantly over the state-of-the-art that was known to us like half a year ago. And it was again surprising to me. Okay, so I think my time is up. Thank you for your attention. Ready for questions?